Gennaro, do you want to do the honors for the next one?
Of course. Yeah, let's move to the next speaker. Let's see. Yeah, so next I'd like to welcome Professor Spring Berman from Arizona State University, who has already joined, and she's a co-host. Amazing. So Professor Berman's research in the field of multi-robot systems ranges from mapping and estimation using robot swarms to collective transport, which I believe is going to be the topic of today's talk. So Spring, I think you can share your screen and take it away whenever you're ready.
Okay.
Great.
Sorry. Just sharing the slides. Okay. Thanks for inviting me to this workshop. So I'm Spring Berman, and I'm an associate professor of mechanical and aerospace engineering at Arizona State University. And so I'm going to be talking today about my group's efforts to develop decentralized control strategies for collective transport of payloads in unknown environments with obstacles, and the various steps that we took and are still taking to get there. All right, so just a brief overview of my lab's research. My lab is the Autonomous Collective Systems Lab, and broadly our focus is on distributed robotic systems. So a lot of the research is on developing scalable control strategies for robotic swarms with very limited information and capabilities, and also stochastic behaviors. We've also done some work recently on decentralized control of soft modular robots with distributed sensing and actuation inspired by octopus arms. And we're also working on human-robot teaming and interactions in multi-robot systems, including traffic testbeds with autonomous vehicles. So there are various and sundry technical challenges for swarm robotics, but just a few to mention here. So swarms might need to operate in denied and inaccessible environments where GPS is not available. There's limited communication bandwidth and range, and communication dropouts, and the robots might not have prior data about the environment, or the environment might be changing. So we want to design robot control strategies that are suitable for long duration operations, where the robots have to make decisions on their own without supervision. And we want the performance of the swarm to be robust in the presence of errors, failures, potentially adversarial inputs. And we want to be able to verify or theoretically prove that the swarm will produce the desired behavior even in the presence of uncertainties and non-deterministic behaviors. So often in swarm robotics, we look to examples of biological swarms that have basically managed to survive and do very complex collective behaviors, subject to these constraints. So some examples here are nest site selection and construction by honeybees and certain species of termites, predation avoidance by schools of fish, flocking is another example. So we want our swarm control strategies to be scalable with the number of robots. And so a way to achieve that is to design decentralized control strategies for the robots. So there, the robots are just relying on local sensing, their own onboard computation, local or no inter-robot communication. Again, we want these properties that I mentioned, that the strategies don't necessarily rely on prior data about the environment, that they're robust to disturbances and failures, that they account for stochastic behaviors, and that they have theoretical guarantees on performance. So I'm going to talk about our work on developing control strategies with these properties, specifically for the task of collective payload transport. And so this is the problem of controlling or designing controllers for a swarm or a group of robots. Oh no, I'm sorry. The fire alarm in my apartment went off. Okay, hopefully it stops. Okay, anyway, so there are various potential applications for collective transport by multi-robot systems. So you can imagine teams of robots that need to move debris during disaster response and search and rescue operations, in manufacturing and construction, mining, logistics, so transport, moving goods around warehouses, and even micro nano robotic applications. So specifically, as a biological model, in
Spring, I think we have a little bit of a broken voice from you. I think.
Okay. I apologize.
Oh, yeah, I think you're back
that
to.
Just.
I think you're back to.
Okay. Sorry, maybe there's too many movies in there. Should I try again to? I'll try again. I'll share my screen.
Yes, please.
Yeah.
Okay. Okay. So I was. So ants are a good model for various reasons. It's they don't have to know about the load that they're bringing back beforehand. They can do this behavior in all sorts of environments, around obstacles and over rough terrain. So we wanted to investigate this behavior. I guess we really started out looking at the biological model. And then in tandem, we also wanted to experimentally verify our strategies. So we built a small mobile robot platform, which is called Pheno, that you can see in the video here. And it has a multi-degree of freedom manipulator arm. So it's capable of doing single and cooperative transport. And so this is just an example. This uses some local sensing, but some centralized commands here to get the two robots to move the payload to a destination. So that's just showing they're physically capable of doing collective transport. So some of the videos of experiments that I'll show use these robots. Okay, so so I'm going to talk about our work on various types of strategies that are decentralized, do not rely on communication or prior information about the environment, the payload, or the robot team. That is like the number of robots, their distribution around the payload. And so in some cases, the robots do not have GPS. So on the left, I'll talk about a couple of ant-inspired strategies for collective transport. And so to start out, I just want to give an overview of the control framework that we're using in order to instantiate these bio-inspired strategies. So this approach uses what's called a mean field model description of the population dynamics. And the mean field model takes the form of, or can take the form of ordinary or partial differential equations that govern the density or population of robots in different states over time. And so the particular mean field model shown here is an advection diffusion reaction PDE that in which you can design the parameters, which are the velocity field, the diffusion coefficient potentially, and the transition rates that govern robot state switching, you can design them using the PDE and then map them onto the robot control policies to basically control the density of robots and their activity over a domain. And so in terms of the collective transport problem, so we formulated this as a mean field model in which the states are populations of free robots that are searching for a payload. And the other states are the numbers of free and occupied zones on the payload, which is represented by these blue and yellow circles here. So the goal that we wanted to achieve is to design the robot probabilities of binding and unbinding from this payload to get target populations of robots around the boundaries. And so just briefly, this is what our control framework looks like, in which we have a macroscopic model with equations that describe these encounter-based interactions of robots with the payload and then their unbinding. And so we can use this to design the probabilities of binding and unbinding in a way that does not require us to measure specific encounter rates of the robots, and in a way that turns out to be robust to a large range of robot populations and numbers of payloads. And so we also had these biological observations of collective transport by ants that are moving a, well, it's a fake food item. It's a dime glued to a piece of foam and then flavored with fig paste, so the ants think that it's food. Stephen Pratt's group took multiple trials of, or videos of different colonies doing this transport behavior. And then from these videos, we extracted data that we fit to a stochastic hybrid system model, where the robots in this, or the ants in this model, are switching between states that are defined as back of the load, front of the load, or detached. So we also coupled it with a simple dynamic model in which the ants are moving this payload and they achieve a target velocity or a final steady state velocity, which is pretty consistent, as we saw from observations. Okay, so
this is a demonstration of.
All right, so we then we translated our biological model of collective transport in ants into a controller that could be implemented on robots. And so in the robot controllers, we also have the guarantees from the mean field model that our system is going to converge, or our swarm will converge to target allocations around the payload. And so we get a similar distribution of robots around the front and the back of our simulated payload, and they also transport it to a target, or ant-like ant scale velocity. And so we can basically use this model to replicate certain features of the ant transport dynamics. Okay, here are some more recent, this is more recent work in which the ants are, now they're pulling, or they're towing on a payload, which is a bunch of straws taped together. And so now they're basically moving just in one dimension, which simplifies the problem somewhat. So what we found is that the data supports the hypothesis that the ant team is moving at the speed of the slowest ant. So now we can incorporate heterogeneity into our ant swarm model, that some ants are maybe more tired or stronger than the others. They're moving at different speeds. And so we replicated this behavior in decentralized robot controllers with different teams of robots. The controllers were based on reinforcement learning algorithms, and the robots have force sensors. So they can adjust their pulling force. And so we found that we could replicate this behavior of the group of robots moving the payload at the speed of the slowest robot. Probably not the most useful behavior if you're trying to get robots to move things around the warehouse or get them to just move something as quickly as possible. But it can potentially accommodate robots with different capabilities or maybe different power levels in order to maybe not get the payload there as fast as possible, but potentially reduce the energy use across all the robots. Okay, so those were a summary of our bio-inspired collective transport strategies. We also developed some controllers that were kind of more loosely inspired by ants, but in the sense that they are decentralized and they rely on only local information. Okay, so we started looking at the problem of collective transport of a payload at a target velocity without any GPS measurements. So the robot team is just given the target velocity to move the payload in, and we also account for the fact that they have manipulators, and they can grasp the payload in any configuration. They're not communicating with each other. They have no information about the payload or the other robots. So what they can measure is their own velocity and heading and their manipulator angle and angular velocity. And so we developed a sliding mode control strategy that we can show will drive the transport team to the target velocity in finite time. And so we verified this with our Pheno robots. So similarly, we looked at a similar problem in which now we tried a decentralized adaptive controller, and we made it compatible with the holonomic constraints between the robots and the payload, so that we can implement it on these non-holonomic mobile manipulators. Okay, so now we introduce obstacles into the environment, and specifically they're convex obstacles. And so now we look at the problem for a single robot of navigating to a target velocity without colliding with the obstacles or getting stuck between them. And the robot does not have GPS. So this is sort of a preliminary step towards collective transport through an environment with obstacles. So here we model a set of obstacles. The robot only knows its velocity, its heading, and the minimum distance from any obstacles in its sensing range. So in this approach, we use a switching control scheme with virtual potential-based controllers. And then we can show that for certain bounds on the parameter of the potential field, that the robot's not going to get stuck on the switching surface between obstacles and that it will converge to the target velocity. So here's a simulation of this behavior and a full trajectory of a robot going through a set of obstacles. And so there's a little bit of oscillation on the switching surface, but the robot does not get stuck. Okay, so some current work that we're doing now is on navigation, single robot navigation and collective transport to a target position in a set of convex obstacles with GPS measurements. So the difference here is that it has to navigate to a target position. The robots can localize themselves. But a lot of the problem is similar in that we don't want the robot or the payload to collide with any obstacles. We want to get the robot or the center of mass of the payload to the target position. Okay, so again, there's no communication, there's no prior information. The robots can measure their minimum distance from obstacles in their sensing range and their position, velocity, and heading. And so the approach that we've been taking is to use a function that's similar to navigation functions in the sense of Riemann and Kodachek, with slightly different properties, in order to prove that the system is going to converge to the target equilibrium position. And so we've done some robot experiments to verify the single robot navigation case. This is actually with a TurtleBot, BurgerBot, rather than a Pheno. Okay, so just to conclude, I guess going forward, we are considering developing controllers in environments with non-convex obstacles, because of course not all obstacles are convex. So we've started looking at collective transport in 3 dimensions. So this is a video from a recent paper where the robots are trying to move this payload to a target position, again, with no communication and no prior information. And of course, we would like to implement our strategies in robots through in environments with obstacles. All right, so I think I will stop there and just acknowledge my lab group and the funding sources that have supported this work. And I'm happy to take any questions.
Thank you. Thank you very much, Spring, for a really interesting talk and for finishing right on time.
Thanks.
So yeah, despite the small accident during the talk. So we actually have already a question, I think I can see on Slido. But maybe before that, let me ask you a question on the future work. You said you're going to work on extending the collaborative transportation with obstacles which are non-convex. Why can't you use navigation-like functions which also work? I mean, with non-convex obstacles. What is the what is the abstraction there?
So I believe it doesn't have the same type of properties that or you can't prove the same. So in navigation functions, the functions are basically, well, they're functions of the geometry or the shapes of the obstacle. So you need to know that beforehand. But in the functions that we're using, there is no knowledge of that geometry. They're only based on the local sensing. And so with those kinds of properties, you can get stuck.
Yeah, so I guess that works like assuming that the obstacles are convex.
Yeah.
Okay, makes sense. Thank you. So let's see. From Slido, I can read you. So this is a question about robustness of implementation of the collaborative transportation with non-holonomic robots. So if there is a small angle error, this could lead to object deadlock. How do you cope with this problem?
If there's an angle error.
Yeah, so I guess like how robust is the implementation of the collaborative transportation when you use non-holonomic robots? You said, I think it's possible to consider those kinematic constraints, I guess, but I think the question was about the robustness of these. Yeah.
Yeah. So right. So we're assuming that the robots can measure, their velocity and their manipulator angle, and manipulator velocity, and but the controller is designed to account for those constraints.
Okay.
Yeah.
Okay. And then another question we can take is, if the robots do not communicate, how do they agree on a direction to move in the last scenario that you show? Do they use force sensing or some implicit coordination?
So that's actually a parameter we're assuming it's given to them.
Oh, okay.
So that's like the reference signal that they're following. Yeah. But you could potentially have them do consensus on a target direction.
Yeah, sounds good. Sounds good. All right, so I think we are right on time for next talk. Is that right, Sid?